Hello, Keith here, and today I'm going to talk to you a little bit about binary, decimal and hexadecimal. Now, this is all relating, of course, to programming. You may hope that you don't need to know too much about them, but unfortunately if you're going to do assembly language, and especially Z80 assembly language, you're going to have to learn it to quite a good extent because you'll need it to do various tricks, and because you've got no operating system to help you out, you need to understand how to convert it for purposes like getting data onto screen in text format. So what I've got for you today, I've got a little tool which I'm going to make available to you. I've got a spreadsheet which is also going to be available to you, and I've got some test code, and I'm going to use these to try and explain to you how hexadecimal and binary work compared to decimal, how you can convert them, and a bit about negative numbers, which really confused me in the early days of programming assembly language. But once you understand them and once you kind of get your head into the way they work, they're actually fairly straightforward. Now, full honesty, I have to admit, I actually got an E at high school mathematics. So if I can understand this, hopefully you can. And I've got all these tools ready, and I think I can give you a really good tutorial today on how it works. And hopefully you'll do as well as I can, if not better. So let's have a look. So what we've got here, I'll just get rid of my Z80 screenshot here. So what we've got here is a little program I've written. This is my website. Please go to my website and look at my tutorials. I'll put a link in the comments below. So you can see we've got decimal, and we've got 4 bits of binary and hexadecimal. Now, if you've never heard of these terms before, I'll explain them to you very, very simply. Now, decimal is, of course, the thing we use every day. It goes from 0 to 10 for each digit, that is. And then the next digit is 10, then 100, and so on. Now, hexadecimal is kind of, if you think that decimal is based on the fact we've got 10 fingers, then hexadecimal would be based on a system of 16 digits, 16 fingers. Now, that sounds pretty odd, but bear with me. Now, binary only has 2 digits, 0 and 1, and this is where it all comes down to. You see, a computer, the way when they designed the computers, they defined everything in cases of on and off because it made them more reliable. So they only had 1 and 0, 1 being on and 0 being off. And when it came to building these ones and zeros into bigger numbers, they started grouping these ones and zeros together. And if we have a look here, 1 digit will be 0, 2 digits will be 2, 3 digits will be 4, and 4 digits will be 8. And 5 digits will be 16. See, you can never clump them together to get 10. So it didn't make sense for them to clump the numbers into 10s like we would prefer. So instead they clumped them into 16s. Now, as I say, this makes things quite frustrating for the human, but for the computer it's brilliant. Now, and if you look at my chart here, what they've done is when they get to 9, they start using the letters A to F. So F is a digit that's worth 15, and B is a digit that's worth 10, in the same way as a 1 is worth, in binary, is a 1 and a 0 is a 0. Now, yeah, I'm sure I'm confusing you already, but bear with me because I've got this really nice tool to help you out. So let's jump straight into my little tool and we'll have a look at it. So I'm just going to reset my emulator here, and I'm going to show you how to load it. So all you need to do is you need to go File, Drive A, Insert Disk Image, and then I'll get this into screen. And I've created a folder called Tools inside the Sources folder, which I'll make available to you. And then all you do, that loads the disk image, and then you do Run and type in Convert. And this starts the program. Now, this program's actually written in BASIC. The reason I use BASIC is because I needed to get this quite quickly. I've only spent a few hours this week making it work, so it was quicker to do it in BASIC, less debugging than doing it in assembler. And I think you'll find it does everything you need, so hopefully the fact that I've kind of cheated a bit and done it in BASIC will be okay. So what this does is this program allows us to view a number. We can type a number in either of the 3 formats, and then we can view it in all 3 formats simultaneously. And this program also gives us a few tricks that we can do to change the number, and because it's showing us all 3 versions of the number, it allows us to visualize the way that those changes affect all 3 numbers. So that probably sounds a little bit confusing, but let me show you. So if I type in D for decimal and type in 32, now you can see 32 is, in decimal is 32. In hexadecimal, it's 20. Now, that's a bit odd. And then in binary, you can see it's a 1 and then a whole bunch of zeros. Now, I should explain this point. This program will go up to 16-bit. This is only an 8-bit number because it's under 256. But and then the thing that I'm hoping will be more useful for understanding this is if you use your cursor keys, you'll see you can move this little arrow. And if you press the tab key, you can switch between each of the bases. I should point out, decimal is called base 10 because it goes up to 10. Binary is called base 2 because it only goes up to 2. And hexadecimal is called base 16. And if you think of those numbers, because later when we're looking at how to convert them, once you understand that binary is base 2, you can use the same code as base 2 and just change the numbers from 2s to 16s, and your code will basically convert a different base. So that's something that's important to remember a little bit later. So anyway, so as I say, I can move my cursor left and right, and what I can do is I can use the cursor up and down to tweak any one of the digits. So you can see here I'm moving the decimal up by 1, and you can see how the binary affects. And let's just have a look. So you'll see 32. All of the binary here are zeros, but when the bits 0 and 1 are zeros. But if I press up to 3, bit 0 becomes 1. Now each bit can only hold 1 maximum. So as soon as it goes too high, in the same way as 9 would roll over into 10, in base 2. It can't go higher than 1, so it goes up to 1, 0. And then another one goes up to 1, 1. And then 1, 0, 0. And if you look at the hexadecimal, as I get up to 9, and then it goes to A, B, C, D, E, F. And then what happens when it rolls over F? There's no G, so it rolls over to 3, 0, 30. Now, I'm hoping that this will give you a bit of potential to visualize how the numbers affect hexadecimal and binary, and maybe it'll let you understand them. Now, I just did that from a decimal number, but this program also allows you to type binary, so I can, if I need to know the binary number 1010, I can just type that in and hit enter. And if I need to know the hexadecimal number 44, or what's 44 in decimal, let's have a look. It's 68. There's a few other little functions here. We can add and subtract. So if I want to subtract, let's say I want to subtract binary 100 from this number, so I press S and press B for binary and 100, and you can see we took that away and we're now down to 64. Now another thing that's quite interesting and quite important that we understand this, because we'll come to this later when I show you my spreadsheet, but if I now press the tab key and move into the binary column, now you'll see that the current unit here is set to 1. That's because binary bit 0 is worth 1. What I mean by that is if there's a 1 in this field, then the total value is 1 is added to the total value, so to speak. So let's move across, and I think that what I tried to explain there will become a bit more clear. So the second bit is worth 2, the third bit is worth 4, and let's go all the way up to the 6th bit, and what a surprise, it's worth 64. Bit 6 is set to 64, it's the only bit that's set, so our value is 64. So what happens if we set bit 1? Well, bit 1 is worth 2, so hopefully you can maybe guess if we set bit 1 to 1, because its current unit is 2, that will increase the value by 2, so it goes up to 66. Now, I think maybe, hopefully, that makes some sense. As you can see, each value is twice what the previous one was. And let's have a look at hexadecimal. Actually, let's have a look at decimal first. Now, we just looked at binary and how the current unit works in that, and it goes 1, 2, 4, 8, 16, 32. Now, decimal, of course, the first unit is worth 1, the second unit is worth 10, and the third unit is worth 100. So hopefully, maybe you can understand now that each digit is worth whatever its base is times the previous one. So base 10 decimal, you multiply 10 by 10, you get 100. In binary, you've got 2, your next bit along is 4 because it's base 2 times by 2. So hexadecimal, our first digit is 1. Hexadecimal is base 16, so we times by 16. The next one's 16. The one after that, well, a bit of hard maths here, but it's 256. And then 4009, 6. And with our 16-bit, that's all we can show. So, as I say, hopefully, using this, playing around with it, seeing how, entering some numbers that you're interested in, maybe this will allow you to get a bit more into your head how these numbers are working. But don't worry if you're still stuck a bit, because I've got the spreadsheet as well, and hopefully between those you'll find a way that you can really get this in your mind. So, okay, let's have a look what else we've got. We've got a few other little functions in this. Now, we're going to look at negatives later, but they're a bit tricky, so I don't want to scare you with that just yet. So we'll leave that for a little bit later. Now, one clever trick that binary and assembly language has is the ability to do bit shifts. And what these are is it allows you to move all of the data from left to the left or to the right. So let's have a go at that and let's see what that does. So I'm just going to press the full stop key here, and you'll see the bits. Well, actually I'll add another bit because it's a bit unclear here. So I'm pressing my full stop key here, and you'll see all the bits have shifted to the left, and I'm going to press my comma key. I said left there, I apologise, they shifted to the right. I'm going to press my comma key, and now they're shifting to the left. And if you watch the decimal digits, we've got 9 here, I press the left key, it doubles to 18. Left again, doubles to 36, and this is really, really important. Doing a bit shift to the left or the right doubles or halves the value of the number. And the reason this is so important is because assembly language has no multiplication or division. So if you're doubling and halving your digits, that's very fast. Otherwise, it's very, very slow. So that's something that's really important to note. Now, I've noticed a little bug in my program here. There are some commands that are missing. There are some, they work, but they're not documented. I'll get those, and so the version you will have the extra line. But if I press the Z key, I'm doing something, and the X key, you'll notice they're shifting again. But this is slightly different. This is actually a rotation command. The difference being, if I keep shifting to the right until this 1 goes off the screen, you'll see it went off 0 and flipped right back into the far side of 7. And this is a trick you can do. If you, rather than shifting to the left 6 times, you can shift to the right a couple of times. By taking advantage of the rotation, you can shift a very small number into a very big number, and sometimes you do need to do that. So that's something that's worth noting, and I'll get this version fixed with that extra bit of text before I upload it. Another interesting tool is there's a assembly language command called CPL, and what that does is it inverts all the bits. Possibly not too clear how that's useful yet, but we'll come to that later. And then I will just add some extra numbers here, and now you can see we've gone all the way up to a 16-bit number here. And you can use the bit shift commands now. The program will detect any number under 256 as 8-bit and do 8-bit shifts, and if it's over 256, then it will treat it as a 16-bit number, and that does slightly affect the way that the program works, but I thought that would be an acceptable way of making it do things to keep it easy but give you all of the functionality you'll hopefully need. So as I say, we can do all of those, and there's another interesting thing we can do. We can actually just look up character codes. So if I just type in a C here, I can look up the character code of C. So possibly not that useful, but occasionally you might need to do something like work out the difference between uppercase A and lowercase a for something you're doing. So I thought it was worth adding in there because it really didn't take too much work for me to add that. So there we go. So as I say, if that's any use to it, I'll make it available. Just aside of that, if you want to use that as your calculator, you can of course, but just bear in mind Windows has a quite fine calculator of its own, and if you go to here, you've got a programmer mode. Mine's Japanese, I apologise for that, but you've got base 16, base 10 and base 2 here. Of course, base 16 is hexadecimal, base 2 is binary. You've even got bit shifts, but I find them a little bit hard to use in the calculator, so I tend to use it for looking things up only. But as I say, it's perfectly powerful, and if it helps you out, go ahead and use it. So there we go. Now let's just get rid of this, and let's just take this out the way and we'll have a look at my spreadsheet, because I think that will help us as well. So this is an XLSX file, but as you can see, I'm opening it in LibreOffice, so don't worry if you don't have Excel. First thing I'll show you is there are some built-in Excel commands which are really helpful for working with hexadecimal and binary and decimal. You've got these dec to hex commands, you've got dec to bin, you've got hex to dec, and so on and so forth. You can look at them for yourself. I should point out both the program I've written and this program, the way I've set it up, this spreadsheet, by default, any extra zeros on the left-hand side are omitted. It makes it a little bit clearer, but in some cases you might find that a bit frustrating. It's a bit difficult to judge. You either add lots and lots of zeros and make it look cluttered, or you take them off, and sometimes it can be misleading what you're looking at. And the hex to bin and the dec to bin commands, you can actually put a comma and type in a digit there and force it to show all those extra zeros if you need them for some reason. So that's something else that this currently doesn't do, but you can of course add if you feel that's the better way of doing things, or if you're doing complex formulas where you need the length to be fixed so that the other parts of the formula work correctly. So here you can maybe see if you type in a number here, then the hex and the bin are automatically calculated accordingly. And if I type in some hex here, you'll see the decimal and bin are calculated. And if I enter some binary, you can see that's calculating. And if I put in something that isn't binary, you'll see you get an error. So again, just a simple little calculator. But the other thing is, as I said, is you can use these functions once you know about them to do some really complex stuff. I created a spreadsheet that was working out color codes and things like that. And so you can use these as a foundation for a much more complex spreadsheet once you know how to use them. So please consider having a look at those if they help you out. Now anyway, let's get back to my discussion about positions, because of the value of individual units. Because as I said before, if you will find there's going to be times where you've got a decimal number in your assembly language. You need to convert that for on-screen use, so you need to work out how to sort of pick out each of the base digits, and so you can represent that on screen. And there'll be times where you may need to take user input in binary or something. I had to do that when I was writing my basic program, and you need to convert that back to a decimal number. So you do unfortunately need to understand these things to a basic level. So right, sorry about that. There was actually a small mistake in the column names here, so I've just corrected that. I only created this spreadsheet today, especially for this video, so a slight mistake there, sorry. Right, okay, so we're back on track now. So let's have a look at the decimal column. As I said before, each unit will be the previous unit times the base number. So with decimal, as you know, 1, 10, 100, each is times 10 the previous one. So we can have a look at that here, and you can see that's what it does. Now base 2 is the same. 1 times 2, previous times 2 times 2 times 2, and so on. With hexadecimal, base 16, guess what? Previous value times 16. Now, if you want to work out any column without working out the previous ones, there is another way of doing it. Now let's have a look here. And what you do is you do the base number to the power of the position. So the first position is 0, and then if you do 10 to the power of 4, you get 10,000 here. And if you do 2 to the power of 2, you get 4. So you can see here, any cell you need to work, any position's value you need to work out, you can do by using the base number to the power of the position starting from 0 and work out that unit's value, and you can use that to then work out the total value in a way we'll see later. So let's have an example then and see if we've got a binary number that we need to convert. So what we're going to do is we're going to convert the value 11101. Let's have a look. And according to our calculator, it's 29. So here we go, 11101. And you can see this is actually written backwards here. And the reason for that is just because of the way I've drawn this spreadsheet. And what we do is we take each column, as I kind of explained before, and we multiply it by the value of that column's unit. If the column is 1, then that value will be added. If it's 0, it won't. And this would still apply with things like base 16. You can do the same thing as well. So here we go, and then this column has a 0 in it, so it's not counted. This one has a 1 in it, and that's times by 4, so you can see here you go. And then your grand total is 29. So there we go. I think that allows us to work out that binary there. And then let's see the reverse. If you've got a start value of 29 and you want to work out the binary, you actually do this in reverse, and you need two division commands. One is a division, a whole number division, which is where the remainder is ignored. So it's kind of an integer division. How many times can I exactly get this from this value? So let's have a look. There's no 1/28 in 29. So the value is 0, and then I'm using another command here, which is the mod command, and that works out the remainder. So then we didn't use there weren't any 1/28, so that's 0. There's no 64s, there's no 32s, but there is a 16. So 1 goes in here, but there's a remainder of 13. And then our next line says, well, okay, that remainder of 13, how many 8s are there in it? Well, there's 1. And then we carry on, so on, until we've got all our digits done. And then if you look down here, or look at it this way rather, you'll see that is our binary number here. And so we have effectively broken down that decimal number into its binary components, and we can now do whatever we want with that binary information. And this kind of thing can be done with base 16 as well, and even stranger bases like base 32 and base 64 you will see in things like encryption, and with when you're converting binary data into emailable data, weird bases like that are used. But the concept's very much the same. You're always working, you're always splitting the data out, working out what each sort of letter or number or whatever your unit is worth times its position, and then rebuilding that into a final number. So hopefully here I've made it a little bit clearer. If I haven't, please have a go with the spreadsheet and with the program I'll give you, and you can maybe figure them out yourself. Now, one thing I haven't explained yet is negative numbers, because unfortunately they are tricky. Now, let's just move this over here, and let's bring in another emulator I've got here. And here it is. And here I just get this in frame. Right. So here you go. We'll just assemble this little program here. And we're going to do, I'm not going to go into the code too much because this isn't a programming tutorial as such. This is an explanation of how hexadecimal and binary work. So let's have a look here. So all I've done is I've started my program, and what we're going to do is we're going to look at how the registers in the memory are affected by the mathematical operations we're doing. Now, WinApe shows all of its registers in hexadecimal, so we'll have a look at that. So the first command is this one, and you'll see we're loading 253 into the accumulator. And what I'm trying to show here is what happens to the accumulator when it goes over the limit of an 8-bit number. So please watch that. So I'm just going to press F7 here to step through. So you'll see now our accumulator is loaded, and then we're going to start adding 1. Ink A adds 1. So we're up to FE, and now we're up to FF. Now FF is 255. 256 will not fit in a 1-byte number. So can you guess what's going to happen when we add another 1 to that? Now let's look. It's gone to 0. And when we do it again, it goes to 1, and it goes to 2. Now, what does this mean? Well, let me explain to you. If you have a value of 255 in a byte number, and you add 1, it's effectively the same thing as subtracting 255 because it goes to 0. because the numbers roll over. Now, that may sound odd, but it's true. I'll say it again. If you've got 255 in a byte and you add 1, it's effectively the same as subtracting 255 because it goes to 0. Now, what you've got to bear in mind at this point is the numbers, what a number means in your program is irrelevant to the Z80. A number could be a memory address, it could be a floating point number, it could be a letter of a word, it could be anything. And in the same way, whether a number is positive or negative is not even known to the Z80, which sounds ridiculous, but let's carry on. So, as I just explained, effectively 1 is the same thing as minus 255 in 8-bit mathematics, because it will turn you back to 0 if you already have 255 in the accumulator. And strange as it sounds, all of the numbers are like this. If you've got a number like 10 and you add 255 to it, you will end up with 9. If you add 255 to it again, you will end up with 8. So 255 is minus 1. And I just need to explain, there's nothing in the Z80 that you say, okay, this 255 is a minus 1. It really doesn't matter to the Z80. What matters is if you're adding 255 to a number that is over 0, it's going down. That's the important thing. And the same works with 16-bit. If you put FFFF into a 16-bit number and add, I'm saying quotes there, and you add it to another 16-bit number that has 100 in it, it's going to go to 99 because it will roll all the way over and keep on rolling over to 1 less than where it started. So that that FFFF is in effect minus 1 in 16-bit mathematics. Now, I'm sure I've probably confused you here, which is why we need this. So let's have a look here. So let's just prove that. So I'm going to change this and I'll type in D and 1. So here we've got 1 in decimal. Now if I press the minus key, you'll see this has now gone to FFFF. As I just said, in 16-bit mathematics, FFFF is minus 1. Now I'm going to press the down key and it will go to minus 2. Well, minus 2 is FFFE. Minus 3 is FFFD, and so on and so forth. Now if this is 16-bit mathematics, but of course F9 will be minus 7 for an 8-bit number. You just ignore the extra Fs, so to speak. Now, I'm sure I've massively confused you all here, but I do fortunately have another demonstration of this. So look at this code here. What we're going to do is we're going to set A to 55, and then we're going to add 255. And then we're going to set A to 55 again, and then we're going to add minus 1. Now, the minus 1 here is converted by the assembler. And if you look here, here we are, you'll see both have actually ended up as add FF, which is this point I'm trying to make about 255 and minus 1. 255 is FF. So 255 and minus 1 in 8-bit mathematics are exactly the same number, which, as I say, confused the life out of me when I started this, but it's true, and it doesn't matter that it's confusing and weird and doesn't make any sense. It's true, it works, so that's it. So let's just see what happens here, just to confirm to ourselves that what I'm saying isn't complete nonsense. So we're going to load A with hexadecimal 37, and then we're going to add our 255, and it's gone down to 36. It has been decreased by 1. And let's just go back. And go back to here, type in decimal minus 1, and you'll see FF is indeed minus 1. So that makes sense. Well, as much sense as it makes. So let's do it again. Oh, press on the wrong emulator there. I apologise. So let's just do that again. So that was the second one, but we know it's going to do the same thing because it's compiled to the exact same bytes. So let's carry on. This time we're going to load 55 and we're going to add FE. Now FE is -2. So you'll see we've gone down to 35. And this time we're going to add FD. Well, what's FD? Well, it's -3. So let's have a look at that. And we're down to 34. Strange, isn't it? Now, as I say, this is probably confusing you and thinking, well, this is all very weird. But and one thing you'll be thinking is, well, hey, if the assembler can work out what these negative numbers are for me, I don't need to worry about it. I'm all right. Well, yes, it can, but there is a bit of a problem with that, with just relying on it. Most of the time, if you always need to subtract 10 from a number, then yes, you can just use your assembler to do it. And of course, just bear in mind, you can always use this as well, and this calculator will do the same thing. Everything agrees what negative numbers look like in hexadecimal, so you're all right there. Of course, the number of F's depend on the bit depth that the software is working in. My program's only 16-bit. This one looks like it's probably 64-bit or something. So, but as I've said before, if you need as many F's as the bits you're working in for your other calculations. If you're working in 8 bits, you only need 2 F's. If you're working in 16, you need 4, etc. Now, as I say, you're probably thinking, well, I can just get the assembler to work out what -27 is. If I happen to need that one day, I don't need to worry about how to actually calculate it. Unfortunately, that's not true, because sometimes you might need to read a byte from the user, or you might need to read a byte from one memory and then apply the negative to another one. So we need to know how to actually calculate it. And I will explain to you, firstly on my little program here, how to calculate it. So let's say we've got decimal 5. Nice easy one. If we want to convert decimal 5 into decimal -5 for our assembler, then what we have to do is we have to flip all of the bits, which is the CPL command, complement. So we flip the bits and then we increase it by 1. And by increase, I mean actually +1. So when we're dealing with negatives, it gets a bit strange. So let me prove that to you. So what I'm going to do is I'm going to press F, and then we've gone to FA, and then I've pressed 1, so now we're at FB. Now, I know what you're thinking. Well, hang on a minute, that says 251, and that's because, as I said before, what something is, whether something's negative or positive, is entirely based on how your program is using it. So let's just confirm that is really -5. So we've got FB there. So if I put decimal and -5, you can see there's a few extra F's, but it's still FB. So my sort of claimed pseudocode there of flip all the bits and add 1 does work. Now, if you're only dealing with 8 bits, then you're in luck, because there's a command that does it for you. There's a nice little command called neg, which negates a number. So let's have a go with that. So we're loading hexadecimal 10 here. So let's get that in here, 10. So that's decimal 16. And let's step here. And it's turned to F0. So let's just confirm that's what will happen then. And here you can see here, the last two hexadecimal numbers here are F0. So yes, that is -16. And then what we're going to do is we're going to load that into B. Oh, I'm sorry, I'm using the wrong emulator again, gets confusing. And then I just skipped a bit fast there. So we loaded hexadecimal 80 into A, and then we're going to add B. But remember, B is actually going to have a negative effect because of that rollover thing. So let's press F7 again, and we're going to see our 80 go down to a 70. If you just look at the accumulator, you'll see what I mean. And yes, it did. Right, so that's how we can do that's how we can convert a positive number to a negative number on the fly in assembly language. But things get more tricky because quite often we'll need to do this with 16-bit numbers, specifically with memory locations. If you've got a relative memory location like my sprites start here and there's a header 100 bytes before that or something, we need to convert that 100 to a minus 100 on the fly. So let's have a go at that. So what we're going to do is we're going to load HL with F000. So let's do that. And then we're going to load BC with 1000. And what we're going to do is we're going to convert 1000 to negative that. So let's have a look in here. So let's do 1000. So that's decimal 496. And then if we press our minus button here, you'll see, interestingly enough, that's going to convert to F000. Now that's pure coincidence, please bear that in mind. It's not anything to do with the previous one that we loaded into HL that we're going to subtract from. But as I said before, the way we convert it is we flip all the bits and then we add 1. Now, because the Z80 is an 8-bit processor, we can't do that 16-bit operation in one go. And there isn't some 16-bit neg command, so we're out of luck there. But we can do it, we just have to do it bit by bit. So what we do is we load B, which is the first part of the number we want to negate, into the accumulator A. So let's do that. And then we use the CPL complement command, which is the same as our flip bits command in my program. And then we put that back into B. And then we want to do the same thing to C. Load it into A, the flip bits command. The flip bits command can only work on the accumulator, you see, that's why we're doing this. And then we load it back into C. At this point, all of the bits in BC are flipped. But remember I said we have to add 1. Now, the BC does have an add 1 command, so we are okay with that. So here we go. We do that add 1. And now you'll see BC equals F000. And as I said before on my emulator, on my calculator, F000 is effectively minus 496 or minus 1000 in hexadecimal. So let's run our add command, and guess what? It rolls all the way over the top, overflows the 16-bit register, and ends up back at E000. So we have effectively minus 100 or 0 or 496. Now, as I say, I apologise for this. You're probably very, very confused, thinking this is madness, what's going on. As I say, it confused me as well, so please don't worry about it. Have a play with my program, have a play with Windows Calculator, have a play with your assembler. I'm going to do another lesson on this, the negatives especially. I'm going to do a proper lesson. I'm going to go into it in more detail than this, which is why I'm not going to give out this source code, because this isn't really finished. I wanted to do an explanation of how binary worked for people who and hexadecimal for people who maybe never even heard of it before, because you need to know the basics for programming. The negative's a little bit more tricky, but I didn't want to create an explanation that didn't cover that, because it's such a unusual thing, and it's such an important thing, because you're never going to get away without subtracting a number ever in assembly. It's just not you're just going to have to do it at some point. So I wanted to make this cover it all, but I will do more about negative numbers in my other tutorials. Well, hopefully we're finished here today. I think we've explained it all as well as we can. So I'm going to put all of this I'm going to upload all of this onto my website into the samples file. And if you like this, please follow my YouTube channel. You know, have a look at the website, maybe look at the other tutorial I've done. I'm going to do a second tutorial very, very soon, just as soon as I can get around to it. Thanks a lot. If you've got any comments, let me know. If you spot any horrendous mistakes I've made, let me know as well.